Okay, so this is definitely one of those lectures that tablet and whiteboard will make a complete hash out of. And this is a little bit of kind of dry theory, but we'll use some of these ideas to do some proofs. So we're going to talk about the integral forms associated with our vector derivatives, and then use that to prove Gauss's theorem, or the divergence theorem, which is essentially Gauss's law. So all the way back to single variable calculus, you have this as the primary definition of the derivative df dx, the limit as delta x goes to 0 of difference in between the function evaluated somewhere and an initial position divided by the distance over which you move it, which essentially the limit as delta x goes to 0 of the secant line gives you the tangent line. So it turns out that all of the vector derivatives have a form that looks like this, in some sense is kind of analogous to this. So the gradient, the divergence, and the curl actually all do. And we're going to just prove one and write the other two down because it's enough to just prove one. So the gradient itself can be defined, and remember f of x, or f is now f of x, y, and z because we're in 3D. I reused x for my single variable example, so shame on me, so I got to correct that. So gradient of x geometrically is the gives you the direction of the greatest descent of the scalar function, and its magnitude gives you the rate of change in that direction. But what you can do is you can define it like this. So first I'll call this delta tau. So not a little piece of difference along my one and only variable x, but a little piece of volume. And what this delta tau really is, in some sense, is a differential piece of volume and then the surface associated with that volume. So let me rewrite that. So this S is the surface of delta tau. So maybe at first we'll think about this as rectangular to make life a bit easy on us. So the interior of this box is delta tau. And the surface of this, the whole surface of it, so imagine you'd have to paint this, is S. Okay. And then the limit as delta tau goes to 0 would tell me the gradient. So in some sense, that's the geometric definition. Although mostly what you know it as is the thing that tells you the direction of greatest descent. Okay. So likewise, we have forms, and honestly, you could probably guess what the divergence and the curl are. Well, maybe not the curl, but the divergence are based on this. They're pretty analogous, so I'll just write them down. And what I'm going to do now, just to get kind of a unified notation, is I'm just going to call this integral d tau is delta tau, because I can. That's what this is. So for a finite piece, and we're going to take a limit as that goes to 0. So the divergence of now some vector function, we don't have a scalar function, can be defined as the limit of this integral delta d tau, where delta tau goes to 0, of this mess. And you can see it's got the right properties. Divergence is a scalar, this is a scalar. And you'll notice in all of these, we're kind of dropping a dimension. So integral ds over volume, so space, volume, space, volume. And then finally, the curl, maybe the one that you wouldn't guess because of this funky minus sign. So you can define the curl of a vector function as the limit as, again, delta tau or integral d tau minus, what? v cross d sigma integral d tau. Okay. And again, for all of these, this is the surface that constrains this, this volume. So there's a second way of writing this that we'll actually also use. And you can actually, if you know Stokes' theorem, you can see Stokes' theorem in this immediately. So we can also define the curl as a circulation with a line integral. And you're like, what's going on with that? It's not a vector. I got to put a normal vector in. And now I've got to, so we don't have volume in a surface anymore. I've got to tell you what this L and this sigma are. So now I have a surface, S, and then this is a closed contour around that surface. And again, if you know Stokes' theorem, you see Stokes' theorem right there. Okay, so not going to prove any of this stuff. We're going to use this for a couple of proofs. Specifically, we're going to prove Gauss's theorem or the divergence theorem. And part of the reason to prove stuff in a mathematical physics class is because you guys will use this sort of technology that's used in the proof to do calculations that are useful for you. And not necessarily because you'll be asked to like prove the thing itself on an exam. Okay, so what we're going to do is actually start by proving actually this, just so you guys kind of see the technology of how something like this might work and introduce some notation. So we're actually going to prove that this corresponds to the original definition of the gradient that you guys see in rectangular coordinates. So our claim is that gradient of f as defined by the limit of this delta tau thing, reverting back to the simpler notation. D sigma over delta tau goes to partial f partial x I hat plus partial f partial y j hat plus partial f partial z k hat in Cartesian coordinates. And before doing that, because this is going to get a little bit hairy, I'm going to introduce some notation. So I'm now going to introduce the notation that f sub x is going to stand in for the partial derivative with respect to x. Likewise, f sub z, for instance, would be the partial derivative of f with respect to z. And this isn't just me, so this is pretty common notation if you're taking partial differential equations class. So we're going to prove this, and to do that, we're going to need a big honkin' picture of this box in Cartesian coordinates. Okay, so what we're going to do essentially is use Taylor's theorem in multiple dimensions, and we'll do this a lot. So imagine, if you will, that I put a dot in the center, and this dot in the center of this box is the function evaluated there is f, and the point itself is x, y, z. Okay, and then this is going to have dimensions, this box, that, not much of a spoiler, are going to be delta x, delta y, delta z, and we're going to ultimately shrink these down into differential sized bits. So these are going to, take a limit as we go to dy, dx, and dz, and get our derivatives that way. Okay, so the first thing to note is that if I want to evaluate this point right here. So I'm on this side of the box, so I'm moving f here. So we'll call this point P. I'm going to claim, and you guys are going to hopefully believe me, is that Taylor's theorem tells me that f of P can be well approximated by f itself. So f evaluated at f x, y, and z. And don't worry, we're going to just kind of collapse the notation really quickly. And then I have to move over by half of delta x. But instead of evaluating this at plus delta x plus half delta x and then delta y, delta z are the same. So actually, let me do this first before Taylor theoreming it. So I could just add, I could just do this. This is what I want. So I'm just going to Taylor expand the first variable of this. So this is what I have to move over by half of delta x. Okay? So f of p, evaluated at that particular point, is well approximated by f of x, y, and z plus f partial x, and then we moved over. So this is the slope of the function in that direction, and then that's how far we moved. So, this is mx plus b. Essentially, that's what Taylor's theorem says in first order. And then I'm going to rewrite that a little bit on the next time I use it. But hopefully that makes sense. If that makes sense to you, what you can do is you can pause and you can figure out, okay, let's say I'm at the top of this box, so now I'm moving up by half delta z. What would that look like? Okay. So there are going to be a lot of terms. I'm not going to write them all. Okay. So what I want to do is I want to evaluate this and then show that it collapses to our usual definition of the Cartesian gradient. Okay. So this surface integral, f integral over the entire surface of f d sigma, how many terms does that have if I were to add them all up? Of course, you're right if you say 6. So this is part of the surface, this is part of the surface, that's part of the surface, and that is part of the surface. So we got 6 terms. They all rhyme, so I'm only going to write parts of them. Okay, call this left. So this is the left panel. So you got a left panel, a right panel, a top panel, a bottom panel, a front panel, and a back panel. Okay. So f minus 1/2 fx delta x. I just split the 1/2 and the x, and I suppress the fact that we're evaluating f at x, y, z. That's super redundant and going to be really annoying. So this is f at x, y, z, and this is partial derivative of f with respect to x evaluated at x, y, z. Okay. I hat plus. So I'm going to write this and then explain why this is true. As long as I do that. Okay. 5 more terms. Sorry, 4 more terms, because this is 1, this is 2. So this is the left contribution to that surface integral. So this is the left panel. What we had to do was evaluate this function at the left panel. And then instead of an integral, so we're basically, we're going to be using the limit sum. So we're going to take delta x, delta y, and delta z in their limits as they go to dy, dz. So we evaluate the function at that point, and then we multiply by the area, right? So think about this as like a Riemann slice, where you evaluate the function at some point, and then you multiply by limit delta x, and then take that limit as it goes to 0. Okay, so that's the left. The right, we moved this function over and then multiplied by the area. So this is the area delta y delta z, delta y delta z. We're going to have 2 more panels of these terms. They're going to be j hat. So that would be the front and the back, and then k hat. And the stuff inside of this is just f, but it's evaluated to be at that front, back, top, or bottom panel. And then here we're going to have delta x, delta z, and here we're going to have delta x, delta y. Right? So area times value of the function. These are essentially like pieces of a Riemann sum. Okay. Why am I doing this to you? So this is why, and these are the important bits that we'll use later on when we do other proofs, is you guys now have the ability to use Taylor's theorem for a multidimensional function. So we'll do this a lot in this class. I have a function evaluated here. I want to like move it in some direction, but now I have choices about which direction I want to move it. So now you can do that. You can use Taylor's theorem. Okay, so I have all these things. It's so horrible. Now I'm going to take the limit as delta x and delta y and delta z go to big delta x, delta y, and delta z go to dx, dy, dz. And then you can follow along at home and multiply all this stuff out. But what you can see is that each one of these terms has a delta x, delta y, delta z. And likewise, each one of these terms will have a delta x, a delta y, that's a y piece, and a delta z. This term will have a delta x, delta y, and then that's the k hat piece and a delta z. What does delta x, delta y, delta z turn into? Well, it turns in into a little bit of delta tau. Okay, so So as we go to infinitesimal limit, we no longer have to use the squiggly equal signs because we're not abusing Taylor's theorem. That becomes exact in the limit for a differentiable function. We end up with something that will look like this. Okay, we're going to have a plus and a minus that cancel in each of those terms. Do something naughty. No, we're good. I actually could have written this in a better way, I think. So there's a minus sign that I could factor out in each one of these. And that actually is a typo. Oh, so this minus sign comes from the dot product. So we have, from the fact that this is one of these points in the plus I direction, one of these points in the minus I direction. So one of these normals is plus I, the other one is minus I. So that was me writing too fast, and then those I could put there. Okay, so we end up with something that looks like this. And finally, so remember that whole exercise was just evaluating the top part of this. Okay, so the top part of that, this integral f dot d sigma, which for a nice rectangular box has 6 terms. We evaluated them. We got this. What's pretty awesome about this differential piece of volume at the bottom, well, that's just dx dy dz. And then we have this whole thing up there. I'm going to save you 30 seconds of your life and not rewrite it. So I'll just say it's there, and you can see the magic that happens. We have these repeated terms, and therefore we have this, which was our putative definition of the gradient is fx I hat f y j hat fc k hat. Or remembering our notation, these are partial derivatives, or df dx I hat plus df dy j hat plus partial f partial z k hat, which is grad f. Okay? So this was kind of the component definition that you learned the first time around when you learned this. This geometrically really is the same thing. So, I mean, that's a proof enough because we used a particular coordinate system. We could have probably done better as far as mathematicians are concerned. But that's good enough because we'll use this in proving vector calculus theorems.